All right, let's talk about the periodic table. Specifically, that big, mysterious block of elements right in the middle, the D block. Now, these aren't your run-of-the-mill elements. Oh, no. You can think of them as the superheroes of the table, packed with some seriously unique abilities that literally shape our world. So let's unlock their secrets.
So, what is it really? What gives these elements their incredible powers? That's the big question we're going to tackle. And you'll see the answer is hidden deep inside their atoms, in a place most other elements just can't match. For one thing, they are the artists of the elemental world. I mean, just think of the brilliant, beautiful blue of copper sulfate crystals, or that intense yellow you get from an iron chloride solution. This explosion of color isn't random, it's a direct clue to their inner workings. And it's not just about what you can see. They've also got these invisible powers. Many of them are strangely, powerfully drawn to magnetic fields. It's a subtle property, but it's a huge hint that something very different is going on inside them. And of course, maybe most importantly, these elements are the absolute workhorses of our civilization. I'm talking about the iron in our skyscrapers, the titanium in our tech. They are the strong, reliable materials that make modern life even possible. Okay, so we've seen what they can do, but how? Where do all these incredible properties actually come from? The answer, the real source of all their power, lies within their electrons, and specifically in the weird way their electron shells get filled. Let's dive in. Okay, so here's the official rulebook definition. A transition metal is any metal with an incomplete d subshell. And that, right there, that's the whole secret. That one little detail, that this particular pocket for electrons isn't totally full, is the key to unlocking everything else. And this is the perfect way to see it in action. On one side, you've got scandium. It has just a single electron in its 3D orbital, so it's incomplete, right? That makes it a classic transition metal. But then look at zinc on the other side. Its 3D orbital is completely packed full with 10 electrons. So even though it lives in the D block, it doesn't quite get to join the superhero club. So this incomplete D shell isn't just a technicality. It's what gives these metals their incredible versatility. It allows them to have a whole rainbow of different chemical identities. Just look at this. It's incredible. On the edges of the block, you have elements like scandium and zinc. They're pretty predictable. They pretty much only have one oxidation state. But then you get to the middle with something like manganese. And wow, it can have 6 common oxidation states, all the way from +2 to +7. That chemical flexibility is their signature move. And why? Why are they so flexible? Yep, you guessed it. It all comes back to that incomplete d orbital. Because it's not full, the energy levels are really close together, which means these atoms can lose or share a whole variety of different numbers of electrons. It gives them a chemical toolbox that other elements can only dream of. And that toolbox is also what paints their world. See, when light hits these ions, those d electrons can get excited and jump between energy levels. When they do that, they absorb certain colors of light, and our eyes see whatever colors are left over. Notice that all the ions with incomplete d orbitals, like titanium, manganese, and copper, are all brightly colored. But then there's our old friend zinc with its totally full 3D orbital. What color is it? Colorless. No room for electrons to jump means no color. It's as simple as that. Okay, so we've seen how their electrons give them chemical variety and all those amazing colors. But what about their physical superpowers? Let's talk about their incredible strength, their magnetic personalities, and their uncanny ability to speed up reactions. So why are these metals so ridiculously strong and hard to melt? Well, most metals only use their outermost electrons for bonding. But transition metals, they bring their inner d electrons to the party too. It's like using way more glue to hold things together. More electrons involved means a much stronger bond, creating a super stable structure that's tough to break apart. And there's a simple, elegant principle in chemistry that just nails it. The more electrons you have available to create bonds, the stronger those bonds are going to be. This is exactly why the elements smack in the middle of the D block, the ones with the most d electrons to share, tend to be the toughest of all. Now, let's get back to that invisible force of attraction. It turns out that any unpaired electrons in those d orbitals act like tiny little magnets. So the more unpaired electrons you have, like manganese here with 5 of them, the more powerfully it gets drawn into a magnetic field. We call this paramagnetism. But look at zinc again, 0 unpaired electrons. It's actually weakly repelled by a magnetic field. It just doesn't have that magnetic personality.
And for their final superpower, they're master matchmakers for chemical reactions. We call them catalysts. So how do they do it? Well, first, their available d orbitals act like a perfect landing pad for other molecules. When a reactant lands, its own bonds get weakened. Then, the catalyst uses its flexible oxidation states to help the reaction happen. And once the job is done, it releases the new products and snaps right back to its original state, ready for the next reaction. It's an incredibly efficient cycle.
But, the story doesn't quite end with the D block. To get the whole picture, we actually have to look down at their mysterious neighbors, the ones usually tucked away at the bottom of the table, the F block elements. Turns out they have a really weird and surprising influence on the superheroes above them.
As you move across that first row of the F block, a really strange thing happens. The atoms actually start to shrink. This is called the lanthanoid contraction, and it happens because those inner F electrons are, well, they're terrible bodyguards. They do a really poor job of shielding the outer electrons from the growing positive charge of the nucleus, so everything gets pulled in just a little bit tighter.
So what's the big deal? What does this actually do? Well, the effect is just wild. Look at this. Zirconium is in one row, and hafnium is in the row directly below it. Logically, hafnium should be way bigger, right? But it's not. Their atomic radii are almost identical. That lanthanoid contraction perfectly cancels out the size increase you'd expect, making these two elements act like chemical twins. It's a bizarre consequence with huge effects.
Okay, so we've been deep in the world of electron shells, oxidation states, and atomic radii. Let's pull all the way back up and connect all this fundamental science to how these elements show up in our actual everyday lives. I mean, the list is practically endless. Their incredible strength gives us the iron and steel for all of our buildings. Their catalytic genius drives countless industrial processes. Their unique electrochemical properties power the batteries in our devices. They're even responsible for the brilliant white pigment in paints and form essential alloys like brass and bronze. They are, quite simply, everywhere. So from their vibrant colors and their magnetic personalities to their sheer strength, every single superpower of the transition metals boils down to one simple, elegant fact. They have an incomplete D subshell. That's what makes them the versatile, indispensable heroes of the periodic table. And it really makes you wonder, if this one block holds so many amazing secrets, what else is the rest of the table still hiding?